Hello, I will begin the vertically integrated project presentation on robust lane detection method against viewpoint variations. I will present in the following order: motivation, method, evaluation, and discussion. Recent days, many deep learning-based lane detection algorithms have been proposed. Based on these advances, driver assistance functions such as lane keeping assist system and lane departure warning system have been commercialized and are now widely used. So the lane detection task is becoming increasingly important. However, when a camera is mounted on a rear vehicle, its height and pitch can vary depending on the vehicle type and installation. As a result, the lane shifts vertically in the image, so the test image looks different from the training images. This domain shift significantly degrades lane detection performance. A shows our experimental results on several lane detection networks. Here, UFLDV2 is clearly faster than the others, while its accuracy is still comparable. However, as shown in B, when we test with vertically shifted viewpoints, the other networks keep their performance even when the lane ratio in the image drops to about 35%, whereas UFLDV2 degrades much more quickly. Next, I will look into the reason for this behavior in more detail. This figure illustrates the hybrid anchor system of UFLDV2. Row and column anchors are placed at predefined positions in the image, and the network predicts where lanes lie along these anchors. This turns lane detection into a classification problem and is very efficient. But because the anchor positions are fixed during training, the model suffers severe performance degradation when the viewpoint changes. We propose an offset head and an alignment block to address this issue and achieve viewpoint robust lane detection. I will explain our proposed lane detection method. When an image whose viewpoint is shifted by D from the source domain is fed into the network, the offset head predicts D and the alignment block corrects the distribution accordingly. Our method is trained in a self-supervised manner. The data loader randomly shifts the original image by D, and this D is used as a ground truth for the offset head prediction D head. The offset head first compresses the backbone feature map along the horizontal direction into column vectors to form a height-wise logic vector Z. From Z, it learns the probability P that the horizon lies at each row H and its prediction D hat, using KL divergence loss and smooth error loss, respectively. Using the predicted D hat from the offset hat, the alignment block performs crop resize on the feature map to make its distribution similar to that of the source domain. Next, I will explain our evaluation. This figure shows the test set we used to quantitatively validate our lane detection method. Starting from the original CU lane images, we gradually reduced the valid lane region from 60% down to 20% in steps of 5%, constructing a 9 test sets. In our experiment, the original UFLDV2 without our method shows a steep drop in performance as the valid lane region decreases. In contrast with the offset head and alignment block, our method still achieves an F1 score of 69.57 even when the valid lane region is reduced to 30%, demonstrating robust lane detection under viewpoint changes. Next are qualitatively results from applying our method in real Korean driving environment. When the valid lane ratio is low, the baseline fails to detect lanes as shown in A, whereas with our method in B, the lanes are clearly detected. Finally, I will move on to the discussion. Our proposed lane detection method achieves strong viewpoint generalization with only a lightweight offset head and alignment block, and the quantitatively and qualitatively results show its potential for deployment in real vehicle. However, although our method improves performance in extremely low FOV cases, it is still very limited when the valid lane ratio falls below 30%. In addition, its generalization to lane detection networks other than UFLDV2 still needs to be verified. Therefore, as future work, we plan to extend the offset head and alignment block to other lane detection networks. Thank you for your attention.